Hello and welcome back. In this video, we'll be discussing something called the kinetic theory of gases. And what the kinetic theory of gases is it's a theory that allows us to relate the temperature of a gas to the average speed of the molecules inside the gas. Now, one thing that's important to keep in mind is that in a real gas, there will be some molecules that will be moving at a higher speed than the average, and there will be some molecules that will be moving at a lower speed than the average. And the only way to get a complete description of what's going on is by looking at a distribution. So on the bottom of the screen here, I give two examples. So on the left, I have the distribution for kinetic energy. So we can see that there are more atoms that are over here that have a lower kinetic energy, and fewer atoms that have these higher kinetic energies. In fact, this distribution over here is an exponential distribution called the Boltzmann distribution. Over here on the right, I show the distribution for the speeds of the particles. And we can see that this increases and then it peaks at a certain speed and then decreases, and there's this long tail. The important thing is just to remember that even though we calculate the average speed of a particle, there will be some molecules that are moving at a higher speed than this and some that will be moving at a lower speed. Now, the first step in finding this relationship between the speed of the particles and the temperature is first finding the relationship between the pressure that is exerted on the walls of the container and the average speed of the particles inside the container. Now, remember, in the very first video, we used the impulse-momentum theorem to come up with a relationship for the pressure that is exerted on the walls of the container and the momentum of the particles. So the way we did this was we said that the average impulse, according to the impulse-momentum theorem, is equal to the change in the momentum. And the average impulse, remember, is defined as being equal to the average force times delta t. So what this means is that the average force that is exerted on a particle when it collides with the walls of a container is equal to the change in the momentum divided by delta t. And according to Newton's third law, the force that is exerted on the wall, let me just write that here, the force that is exerted on the wall is just going to be minus this. So this is the force that is exerted on the wall of a container when a single molecule collides with the container. Now, of course, there are a very large number of molecules inside the container, and there's going to be a very large number of collisions per time delta t. So the total force, or the average force that is exerted on the wall of the container after some time delta t is going to be equal to the number of collisions that occur times the average change in the momentum of the particle during each collision divided by delta t. Or another way of writing this, of course, remember, was minus n divided by delta t times the average change in the momentum, where this n over delta t describes the rate at which collisions are occurring. Now, one thing I want to point out about this equation is it should be obvious that this will depend on the speed of the particles, because the faster the particles are moving, the larger delta p will be, the larger the momentum change will be when it collides with the wall, and also the faster the particles are moving, the more frequent the collisions will be. And so, to understand how these things are related to the speed, I want to look at a very, very simple example of just a single molecule that's bouncing back and forth between two walls in this very simple linear motion that I have shown here. So, the amount of time it takes for the particle to collide with this wall, go all the way to the other side of the container, and then back so it collides a second time, is going to be equal to, so we have v is equal to delta x divided by delta t. And if the container has a length of L, then the amount of distance it has to travel to go through one round trip, so it's going to travel all the way to one side and then come back, so the distance it will travel is 2 times the length of the container during a time delta t. So the time between collisions, delta t, is going to be equal to 2 times the length of the container divided by the speed that the particle is traveling at. Now, if we think about this, if the particle bounces off the container in an elastic way, so it's moving with a speed v, and then it hits the wall, and then it's moving in the opposite direction with the same speed v, then the change in the momentum of the particle is equal to m times the change in the velocity, and this is going to equal 2mv. And we found that the amount of time it takes between collisions is equal to 2L divided by V. So by combining these two equations, so we found before that the average force is going to be equal to n over delta t times the average change in momentum. So in this case, this particle is going to exert a force. So if I had a whole bunch of particles and they were moving back and forth left and right like this, then the force that would be exerted would be equal to n divided by delta t, so that's 2L divided by v, times the change in momentum, and that's 2mv. So in other words, this is going to be n times, the 2 here will cancel with the 2 here, this v will come up to the numerator, so I'm going to have n times mv squared divided by L. So this is the average force that would be exerted by n particles if they were just bouncing back and forth going left and right like this. Now of course, in reality, the particles are going to be moving in all sorts of different directions, so obviously the change in momentum is going to be less than 2mv, because sometimes the particle is going to come in at an angle like this and come off at an angle like that, and so the change in momentum will be less than 2mv. It's just going to be 2m times that x component of the velocity. And because there are 3 different directions, it turns out that the average force is just going to be 1/3 of this. The average force that is exerted on the wall of the container is just going to be equal to n divided by 3 times m times the average of the square of the velocities divided by L. So in the previous slide, I had just the square of the velocity, but as I mentioned at the very beginning of this, each of the particles will be moving at different speeds. So if I'm looking at the average force and each of the particles are moving at different speeds, what I want to plug into here is the average of the square of the speeds. So that's what these angled brackets mean. That means I'm taking the average. Okay, so this is the average of the square of the speeds. So that's basically what I'm just saying here. One thing that is important to understand about the average of the square is that it's not exactly the same thing as the square of the average. In fact, if we think about the velocities, a particle is just as likely to be moving up as it is to be moving down, and that's true for any direction. It's just as likely to be moving left and right. So if I take the average velocity, on average all these directions will cancel out. So the average velocity of a particle is always going to be 0. So if I take the square of the average velocity, I'll get 0. So this is why we always take the square, or we take the average of the square of the velocity, because this will be some non-zero number. So remember that the force that is exerted on the wall of a container is not really a property of the gas, because the larger the container, the larger the force that is exerted on it. So what we want to look at is the pressure. Remember, pressure is equal to force divided by area. So we found that the force is equal to n divided by 3 times mass times the average of the square of the velocity divided by the length of the container, and we're going to divide this by A. Now if we think about this, the length of the container times the area of the wall of the container is equal to the volume of the container. This over here, this thing in the bottom is equal to the volume of the container, so this is n divided by 3 times the mass of the particles times the average of the squares divided by the volume. Now we have to be a little bit careful when we're dealing with this equation, because we have these 2 v's here, so we need to be careful not to get confused. This big V down here is the volume, and this little thing here is the speed of the particles. So now what I want to do is I want to combine this with the ideal gas law. Remember at the beginning of this I said I wanted to relate the speed of the particles to the temperature. So what I can do now, so we have over here, we have P is equal to n divided by 3 times m times the average of the squares divided by the volume. So let me go ahead and just multiply both sides by volume. If I do that, I get PV is equal to n over 3 times m times the average of the square speeds. And we know, according to the ideal gas law, PV is equal to nkt. And in the previous slide, I found that PV is equal to n/3. So we have this is equal to n divided by 3 times m times the average of the square of the speeds. So in this case, the n's are going to cancel out, and I see that kt is equal to 1/3 m times the average of the square. And typically the way we write this is we write the average of the square, the speeds, is equal to 3kt divided by m. And so typically the way that we write this is we take the square root of both sides and we call this number over here. So think about what this is, okay? this is the square root of the average of the square of the speeds. So we call this the RMS. It's the root mean square, because it's the square root of the mean of the square of the speeds. So we say the RMS speed is equal to the square root of 3 kT divided by m. Now, recall that we can relate the molar mass to the mass of a molecule. So remember, anytime you take a big letter, it's equal to Avogadro's number times the small letter. So this is big M molar mass is equal to Avogadro's number times the mass of a molecule. We also have that R, the ideal gas constant, is equal to Na times K. So if I plug these into this equation, so here we have that RMS speed is equal to the square root of 3 kT divided by m. So now if I plug m is equal to big M divided by Avogadro's number, and I plug that k is equal to r divided by Avogadro's number, I have 3 times r divided by Avogadro's number times T divided by the molar mass divided by Avogadro's number. And we see that the Avogadro's number cancels, so that this is also just equal to 3RT divided by the molar mass. And usually this is an easier equation to use, because what you'll be looking up when you solve a problem like this is you'll be looking up the molar mass in the periodic table. Now, again, I want to caution you about the periodic table. The one thing you do need to remember about when you look up the masses, the periodic table of elements, is that the mass that you look up will be measured in grams. Okay? A good way to check your answer is that the RMS speeds are typically going to be in the hundreds of meters per second. If you're getting a speed that's like 4 or 5 meters per second, chances are you forgot to convert the mass into kilograms. So we found the RMS speed. Kinetic energy, remember, is equal to 1/2 mv squared. So using this equation, we can also find the average kinetic energy. So the average kinetic energy of a single atom is going to be equal to 1/2 mv RMS squared. And that's approximately going to be equal to 3/2 times nRT. So now that we have a formula that relates the average speed of the particles inside a gas to its temperature, we can use this relationship to calculate the average kinetic energy as a function of the temperature. So remember that kinetic energy is equal to 1/2 mv squared. So the average of the kinetic energy is going to be equal to 1/2 m times the RMS speed squared. And for a single particle, the RMS speed is equal to the square root of 3RT divided by m, or 3 kT divided by m. So we could write this as 3 kT divided by the mass of a single particle. And if I do that, the m's cancel, and we see that this is equal to 3/2 kT. So this is the average kinetic energy of a single particle inside the gas. Now if I have n atoms in the gas, then the average kinetic energy of the entire gas is going to be equal to n times the average kinetic energy of a single molecule. So we get 3/2 nkt. So this is the average kinetic energy of n molecules in a gas. So now let's go ahead and look at a simple example. This example says that air mostly consists of nitrogen gas. So this is N2. That means there are 2 atoms of nitrogen in the molecule. And the question asks us to determine the RMS speed of N2 at room temperature, which is 15 degrees Celsius. So remember that the RMS speed, so VRMS, is equal to 3RT divided by the molar mass square rooted. So the first thing we'll need to do is we'll need to look up the molar mass in a periodic table. So if we look at the periodic table, we see that the molar mass of nitrogen is equal to 14 grams per mole. So what I need to do is I need to plug into this, m is equal to, actually we need to be a little bit careful because we're looking at molecules of nitrogen. So remember that this is the molar mass of nitrogen is equal to 2 times the molar mass of nitrogen atom. So that's going to be 2 times 14. And we need to be careful, this is grams per mole. So this is 28 grams per mole, or 2.8 times 10 to the minus 2 kilograms per mole. And if I plug this number into this equation up here, I'll see that the average speed is equal to, I think it's 506 meters per second. So we can see that the average speed of even, just air at room temperature is extremely fast. And so at this point, I think I'm going to end this video, and this will end our discussion of ideal gases. And in the next video, I'll talk about how we can convert this thermal energy, this random motion of atoms and molecules inside a gas, into useful energy using engines and things like that.